Okay. To all of you for coming here to join this special session for my retirement celebration. Because some of you probably are not so familiar with me, so I would like to introduce myself briefly. Master degree from National Yeong-Maw University in Hsinchu, Taiwan, in 1981 and 1983 respectively. After I earned my engineering doctorate from the University of Tokyo in 1990, I went back to Taiwan and started my academic job in National Song-Jeng University, SYSU, from 1990. So up to now, I have been working in SYSU for about 35 years. So it can be said that I have devoted to my whole academic career to SYSU. And I have ever served as department chair in SYSU for 2 terms, totally 6 years in 1990 and in 2005 and 2020. And I have ever been a visiting professor in Ohio State University in 2006 and 2000 years. About the paper publications, I have 180 journal papers published and totally 220 conference papers. And about 1/2 is international conference paper. I also got 32 invention patents or technology transfer, published 6 books. About the PI project from STC of Taiwan or industries, I implemented 115 projects, and total project grant about $3.8 million US dollars. It's not so much compared to other countries. Professor Hwang has a very big project grant, about 30 million, $30 million NT dollars per year. And about the graduate from my laboratory under my supervision, there are about 7 students for doctor degree and 120 for master degree. And it happened that my PhD student, Professor Zhong, and my last I was honored with the title of Fellow of Japan Society for Technology of Quality, JSTP, in 2012. And I earned Distinguished Professor of SYSU in 2012. And I was one of the world's top 2% scientists in 2022 and 2023. And I'm interested in the fields of plasticity, metal forming, variable structural control theory, maths, and so on. And my research are mainly focused on metal formings, including tube isoforming, rolling extrusion, lattice drawing, hot rolling, and forging. And tomorrow I will present a keynote paper about hydro joining and hydro drawing of stainless steel and microtube. Okay. I would like to thank all of you for coming here again, and especially to the speakers present their papers in this session. I would like to appreciate Professor Song-Jeng for lending me 5 minutes. Okay, thank you. Thank you very much.
Invited him and to do the keynote speech, and he want to talk about his topic, application of the tube hydroforming to the hydro piercing, hydro joint, and hydro joint. Now welcome to Professor Hwang. Welcome.
Thanks for the chair's introduction for me. It's great my honor to present this keynote lecture, applications of tube hydroforming to hydro piercing, hydro joining, and hydro drawing. My name is Yeong-Maw, working for National University in Taiwan. What is tube hydroforming? Hydroforming can be defined as a process to conform the hollow part with different cross section by applying the internal hydraulic pressure and forcing the tubular length to conform to the shape of a given die cavity. And because of no need of the internal die in tube hydroforming process, no friction at the inner surface of the tube, and the complex hollow shape and the lightweight product are its features. Comparing to traditional manufacturing via stamping and welding, tube hydroforming offers several advantages, such as part consolidation, weight reduction, improvement of structural stability, and increase of the strength and the stiffness of the form parts, more uniform segment distribution, fewer secondary operations. However, this technology is suffering some disadvantages, such as slow cycle time, expensive equipment, and the lack of extensive knowledge base for tooling and process design. In this lecture, 6 topics about applications of tube hydroforming are to be presented. At the first, a tube hydroforming system is introduced. The second is an adaptive control algorithm is proposed to determine the loading path for T-shape hydroforming process of products with different outlet diameters. And the third is a hydraulic compound forming process, combining conforming, crushing, and hydro barging is proposed to manufacture rectangular tubes of aluminum alloy. The fourth is an application of tube hydroforming to manufacturing of multi-convolution metals. The fifth is hydro piercing, hydro joining of aluminum alloy tubes. At the last, hydro drawing of stainless steel microtubes will be introduced. A tube hydroforming system generally includes the following subjects: the tube material property and the dimensions, the capacity and the rigidity of equipment, the shape and the dimension of the design of the tooling and the dies. The loading path design of feeding speed and internal pressurization, the friction coefficient determination at the interface between the tube and the die, the measurement of dimensions and the mechanical property of the formed products. My presentation is mainly focused on the design and the loading path design in tube hydroforming process. In 2003, MIRDC, Metal Industry Research and Development Center, collaborated with Giant Manufacturing Corporation and applied tube hydroforming technology to manufacture bicycle components, such as handlebars, lugs, and supporting branches of aluminum alloys. MIRDC also developed tube hydroforming of bathroom accessories like bellows, lamp structure, and faucet components. The second topic is T-shape hydroforming process for products with different counter outer diameters. The contents have been published in Journal of Engineering Manufacture in 2015. This figure shows a schematic diagram of T-shape hydroforming process with the tube diameter D0 and the bench diameter BP. The surface. Yeah, the surface of the billet is designed with an elliptical curve of axis I and RV. The hydroforming process is divided into two phases, batch stage and bench protrusion stage. In the batch stage, a hydraulic media is input through an entrance hole to generate a high pressure, PI, to batch the tube simultaneously with the action of the two pushing punches. And the counter punch is kept still. In protrusion stage, the counter punch starts to move backward at a constant speed. A flow chart for the batch stage is shown in the right figure. At the first, the following parameters such as the material property, the geometry, internal pressure equipment, axial feeding equipment, and so on are input. At the early batch stage, the thickness ratio at the top of pressure P is checked. If it is smaller than 90%, the internal pressure is increased. The actual feeding moves forward by one step, and then the simulation is iterated. Outer P is in contact with the counter punch. The process proceeds to the later body stage, and the separation at the die fillet and the wrinkling at the guiding zone are checked. If yes, the internal pressure is increased, the actual feeding moves forward by one step, and then the simulation procedure is iterated. After the contact length ratio reaches 80%, the simulation goes to the bench protrusion stage. And this loading path obtained by the adaptive control algorithm for different branch diameters are shown in these figures. The tip diameter is 60 millimeter. The die fillet radius is 15 millimeter. The loading paths are divided into batch and protrusion stages. The actual feeding speed is set as 0.06 millimeter per second, whereas the counter punch speed is set as 0.0 0.026 millimeter per second for branch diameter of 20 millimeter. Because more material volume is pushed into the die cavity for branch diameter of 40 millimeter, a faster counter punch speed of 0.034 millimeter per second is set. The appearance of the hydroform products for different branch diameters are shown in these figures. Clearly, some products without any defects are obtained for all cases. Experiments of T-shaped tube hydroforming were conducted using this self-developed hydroforming test machine. This test machine consists of four main parts: a platform for supporting the tooling, a hydraulic power system for providing the pressure source of the internal pressurization, three motor-driven pushes for the axial feeding and the counter punch, and a PC-based control system. This test machine can operate with up to 50 megapascal for the internal pressure, 50 tons for the pushing force, and 300 degrees C for the forming temperature. The comparisons of the thickness distribution at the upper portion of the formed product between the predicted and the experimental data are shown in the right figure. The branch height obtained is 25 millimeter. The minimum thickness occurring at the top of the branch is about 90% of the initial tube thickness, which meets the requirement of industrial applications. Because the actual internal pressure was slightly smaller than the prescribed value, the actual thickness at the top of the branch was slightly larger than the predicted value. Generally speaking, the numerically obtained product shape or profile and the flow line configuration are quite close to those obtained experimentally. And the third topic is hydraulic compound forming process of rectangular tubes. The patents have been published in International Journal of Advanced Manufacturing Technology in 2016. The compound forming process consists of preforming, crushing, and hydroforming. The preforming process is used to change the tube shape and make it be able to be input into the hydroforming die sets. A circular tube with a diameter D0 and the thickness T0 is preformed by two pressing plates and becomes an overlap tube with a short axis W and a long axis H. The configuration of the preformed tube and die sets for crushing and hydroforming before and after forming are shown in figures A and B respectively, where delta is the initial gap between the upper and lower dies. A and B are the height and the width, respectively, of the formed rectangular tube with the corner radius R. At the late stage, the internal pressure is increased to calibrate the tube and make the tube material flow into the corner of the die as much as possible. The pressurization profile is divided into two stages. At the first stage, a constant small internal pressure PA is input to make the void between the tube and the die as small as possible. At this stage, PA cannot be too large, otherwise the tube would move outward and result in pinching of the tube between the upper and the lower dies. The void generation stroke SA increases with the internal pressure PA, which means void generates early when PA is smaller. When PA increases from 0.6 to 0.7 megapascal, SA increases dramatically from 2.8 to 4.5 millimeter At the stage 2, a larger internal pressure is input to compress the void and is increased gradually to PV to make the tube material flow into the corner of the die as much as possible. These figures show the effects of internal pressure, PA, on the signal distribution of the product for PV equals 10 megapascal. Clearly, a quite uniform signal distribution of the product was obtained when PA equals 0 and 0.5 megapascal. As PA equals 0.7 megapascal, the larger thickness variation occurred at the 4 corners. A corner radius of 6 millimeter and quite uniform signal distribution can be obtained with PA equals 0.5 and PV equals 10 megapascal. A linear loading path used for the compound forming experiments is shown in the left figure. A counter punch feeding was used to push the upper die to crush the tube, and two axial feedings were used for all the sealing in the two ends of the tube. The movement of the counter punch is faithfully followed the prescribed positions because the internal pressure was controlled manually. Some variations in the pressurization curve was observed. The average values of the experimental presentation curve approximately followed the prescribed one. When no internal pressure was input into the tube during the compound forming experiment, the tube could not be formed into a rectangular shape. When the final pressure was set as PV equals 5 or 8 megapascal, some product with rectangular shape was obtained. The fourth topic is tube hydroforming of multi-convolution bellows. The contents have been published in International Journal of Advanced Manufacturing Technology in 2023. Metal bellows are generally manufactured by compound forming with hydroforming. Metal bellows have been widely applied in various industries, such as chemical plant, power system, heat exchangers, scale sealing elements, and so on, for absorbing the irregular expansions of the pipes, damping vibration of the circumstance and the mechanical movements. This figure shows the geometry and dimension of multi-convolution bellows, where H is the height, W is the pitch, Ti is the thickness, Lb is the length of the bellows. The arc radius at the top and the bottom of the convolution are R1 and R2 respectively. E0 and T0 are the diameter and thickness of the tube respectively. The dimensions for each part of the bellows used in the simulation and experiments are given in this table. The acceptable ranges for convolution height and the thickness of the bellows are 5 plus minus 0.25 millimeter and 1.2 plus minus 0.12 millimeter respectively. And this figure shows the geometric configurations between movable dies and the tube in each stage. The loading path for simultaneous feeding pipe is shown in the right figure. For the movement of the die set, generally the first die D1 is pushed forward by a punch. The second and third dies D2 and D3 are also moved forward simultaneously by the punch through a specially designed mechanism or a spring system. An orifice was designed at the first movable diaphragm to let hydraulic media flow into the tube to budge the tube. LT is the initial die gap between the movable dies. HD is the die cavity height to prevent the tube from being pinched by the movable dies at the late stage of the process. TD was set at 6 mm. At the first stage, only a small internal pressure is applied into the tube to make the tube bulge outward. At the second stage, the three movable dies start to move forward simultaneously to make the tube material flow into the die cavity. At this stage, the material pressure can be adjusted. At the final stage, the movable die are closed completely, and if needed, a higher internal pressure is input to make the convolution reach the desired height. The hydroforming process using sequential feeding type is also divided into 3 stages. The geometric configuration between the movable dies and the tube, the initial state and the first stage, are the same as those using the simultaneous feeding type. At the second stage, the first movable die D1 starts to move forward to complete the formation of the first convolution. Then the first and the second movable dies move together to complete the formation of the second convolution. And finally, all the 3 movable dies move together to complete the formation of the third convolution. At this stage, dies 2 and 3 are moved passively and pushed forward by die 1. So the formation of the convolutions is completed sequentially, not simultaneously. A commercial finite element software different 2D was used to simulate the hydroforming process. The tube material used was stainless steel 304. An isotropic and electroplatic material real model was set for the tube material. Tensor tests were conducted to obtain the flow trace of the tube material. Totally about 6,000 quadrilateral elements were set for the tube. The minimum element length is about 0.13 millimeter. There are 8 element layers in the same direction of the tube. The mesh configuration in the tube and the geometric configurations between the tube, movable die, and the fixed die before hydroforming are shown in the right figure. And these figures show the effects of internal pressures on the convolution height and the second distributions of the formed barrels. In tube hydroforming of multi-convolution barrels, a too low internal pressure probably resulted in defects of Lincoln, whereas a too high internal pressure may result in oversealing in the formed barrels. For PI larger than 30 MPa, quite uniform convolution height is obtained, and the convolution height increases with the internal pressure. From the thickness distribution diagram, clearly the thickest position occurred at the bottom or belly of the convolution, and the thinnest position occurred at the top or summit of the convolutions. The minimum thickness for internal pressure of 50 MPa is smaller than the minimum requirement of 1.08 millimeter. This figure shows the effect of internal pressure on the average convolution height and the minimum thickness using simultaneous feeding type. The average convolution height increases with the internal pressure, whereas the minimum thickness decreases with the internal pressure. For PI equals 30 and 40 MPa, the average convolution height located at the acceptable region and the minimum thickness is larger than the acceptable minimum value. Hydroforming experiments of multi-convolution barrels with sequential feeding pattern were carried out using this self-developed hydroforming machine. This machine has a capacity of 100 megapascal for internal pressure and 30 pounds for the pushing force and 200 millimeter for die pushing stroke. This machine is composed of 4 main parts: an upper and lower die set, a control system, a hydraulic power unit, and the pressure booster were used to increase the internal pressure from 30 megapascal up to 100 megapascal for budging the tube. Stainless steel 304 tubes with an outer diameter of 40.4 millimeter were used as specimens in the hydroforming experiments. Before experiments, the tube thickness distributions were measured and some variations of 1.13 plus minus 0.05 millimeter in the circumferential directions were found. The thickness position occurred at the welding line. After experiments, the hydraulic bellows were cut into two halves in the longitudinal direction using electric discharge wire cutting for measuring the thickness distribution of the formed bellows. The comparisons of the convolution height and thickness distributions between simulation and experiments are shown in this table and this figure respectively. The maximum errors for the convolution height and the thickness between simulation and experiment are about 3% and 5% respectively. The fifth topic to talk is the hydro-piercing and hydro-joining. And the contents have been published in journal materials in 2025. And this study proposed a novel tube hydro-joining process which combined piercing, hole flanging, and the nut inlaying. The nut punch-shaped design proposed by this paper can deliver three advantages of no scrape, no oil leakage, and a longer flange length, which can achieve stronger cramping force and accordingly increase the pulling out force. Concerning the study of hydro-piercing process, our research group has proposed a punch-shaped design and investigated the effects of various parameters such as punch stroke, internal pressure, on tube deformation and fracture mechanism in tube hydro-piercing process of carbon steel tubes. This figure shows the contact configuration between punch and tube. And this figure shows the contact configuration between punch and the tube before and after hydro-piercing. Liu et al. Proposed a punch-shaped design and investigated the effects of punch shape on geometric profile and the quality of pierced and the flange holes by experiments and simulations with three different shapes of transition zone between the piercing punch and the flanging punch. Concerning hydro-joining process, Mizumura et al. Proposed a compound process, combining hydro burning and nut inlaying with a designed punch shape as shown in these figures. However, with this method, the pierced scraps may result in blocking of the oil pipe and cause fluid flow problems. On the other hand, oil leakage around the punch surface may occur in hydro-piercing and hydro-burning process, which lead to the pressure drop of the internal pressure. In this paper, the novel hydro-joining process combining
piercing, flanging, and inlaying was proposed. The punch net shape design proposed by this paper can deliver three advantages of no scrap, no oil leakage, and longer flange length. The hydrogen process comprises 5 stages. At stage 1, the internal pressure was applied to span the tube into the desired shape, establishing internal support. In stage 2, the punch shape nut moved downward to flange the aluminum alloy. In stage 3, the internal pressure was released to enable sufficient tube material elastic recovery during the inlaying stage and ensuring adequate clamping force. In stage 4, the punch continued to move downward, invading the punch-shaped nut. Finally, in stage 5, the punch was retracted upward, having the nut in place, leaving the nut in place. For clamping force tests, the punch and the nut were retracted together to determine the pulling out force. The nut shape consists of 3 zones. A conical zone designed for piercing and preventing fluid leakage during the flanging process. A parallel zone designed for flanging the hole with a diameter of 6.9 millimeter and a height of 4 millimeter. The design ensures sufficient contact area and the contact pressure between the hole flange and the nut. So, to prevent the fluid leakage from the hole, the fit zone designed to enhance the clamping force during the inlaying stage. Detailed nut shape parameters are listed in the left table. An implicit and static finite element code, Form 3D, was applied to analyze the electroplatic deformation pattern of an aluminum alloy tube during hydrojoining process. The tube and the die were regarded as rigid bodies and tube is electroplatic. Tensor tests were conducted to obtain the flow stresses of aluminum alloy 6063 at different strain rates, as shown in this figure. And normalized the Cockcroft-Layson fracture criteria was used to predict if the tube is pierced through by the nut or not in the hydrojoining process. The critical damage value for a near 6063 was set as 1.42 from literature. Due to symmetry on the left, right, and the front back sides, only 1/4 of the objects was adopted in the simulations to save the simulation time. 1/4 of the tube is divided into 3 zones, which have different element size ratios, set as 0.2, 0.4, and 1 for zones 1, 2, and 3 respectively. The tube material in zone 1, just below the punch head, undergoes most severe plastic deformation. Thus, a smaller size ratio was set in this region. Convergent analysis was implemented to determine an appropriate element number for saving the simulation time with an acceptable simulation result error. As the total element number increases to 60,000 elements, the relative difference in the maximum punch force decreases to within 0.5%. Accordingly, approximately 60,000 tetrahedron elements with a minimum element size of 0.2 millimeter was set for the tube object in the following finite element simulations. To investigate the effects of the geometric parameters of the not fit zone on the pulling out force during the hydrojoining of aluminum LE6063 tubes. Simulation were conducted using various internal pressures, fit zone height, and knot diameter to explore the effects of tapered loading paths under different strokes. Under different slopes. In the simulations, the punch load began at point A, as the knot moved downward for hydroflanging. At the point B, the punch load reached its peak as the parallel zone began to pass through the hole. At point C, the fit zone of the knot began to enter the hole. At this stage, the knot temporarily ceased its downward motion, and the release of the material and the internal pressure resulted in a sharp decline in the load. After that, the knot resumed its downward motion to begin delaying. Finally, in point D, the punch began to withdraw until point E using a reversed load shown with a negative value. These figures show the maximum pulling out force or drawing force for different fit zone diameter, fit zone height, and the different internal pressure levels. At the internal pressures of 40, 50, and 60 megapascal, the drawing force decreases as the diameter increases from 7 millimeter to 7.2 millimeter. The results suggest that the best fit zone diameter is 7 millimeter. For hydrojoining experiments, a custom designed upper and lower die set was employed to integrate the hydraulic system, servo press, load cell, and tube holding sleeve. The upper die set served as the punch mechanism for driving the nut downward. The lower die set was used to secure the tube connecting to the hydraulic pipe and position the upper die set. Before the experiment, the tube was pressed into the tube holding sleeve at the lower die set. The hydraulic system delivered hydraulic fluid through oil pipe and plugs into the tube inside the tube holding sleeve at the lower die set. On the basis of simulation results, hydrojoining experiments were conducted with a fit zone height of 7 millimeter and a knot diameter of 7 millimeter and the hydraulic pressures of 30 megapascal and 50 megapascal. The tube material used was annealed aluminum 6063 with a length, diameter, and thickness of 83, 50.8, and 3 millimeter respectively to fit the die dimension. The right figure shows the loading path between punch stroke and the internal pressure during the experiments. The curves in this figure indicate that the experimental loading paths were consistent with that in the simulations. Because the servo press was manually operated during the experiments, the loading paths exhibited some delays with respect to the loading path. In the load figure, Point A represents the maximum load induced by the downward movement of the nut and the internal hydraulic pressure. Point B represents the load reduction after the hydraulic pressure is released. Point C represents nut repunching during inlaying stage. Point D corresponds to the maximum pulling out force as the punch retracted or moved backward appear with a negative value. These tables show the comparisons of maximum load and maximum pulling out force between simulations and experiments. The error in the maximum load result was approximately 20%, indicating that the experimental results was consistent with those of the simulations. The error in the maximum pulling out force was larger at 30 MPa, approximately 50%, whereas the error at 50 MPa was only 5%. The lower figure shows the comparisons of the appearance of the cross section between the experiments and the simulations. The flange edge length in the simulations was larger than that in the experiments because in the simulations the material flowed outward, forming a flange by the round corner of the nut and ruptured at the nut tip. In the experiments, the rupture zone clearly appeared near the nut's parallel zone, resulting in a shorter flange length and waste material. The rollover in the experiments was also significantly larger, possibly due to the lack of internal pressure support after the pressure release during the nut inlaying stage. An M5 nut was designed to prevent the nut from being pulled out along with the punch during the retracting stage. To achieve this, a strong magnet was added above the nut to prevent separation of the nut and the punch due to gravity. The right figure shows the appearance of the inlaid nut for 3 different pressures. Inlaying process at all 3 pressure values were successful. A bolt was screwed into the nut as shown in the left figure. For no internal pressure, no noticeable rollover was present on the surface. At the 30 MPa, a slight nearly invisible rollover was present. At the 50 MPa, the surface was completely flat, indicating optimal homogeneity. And the 6th topic to talk is hydro drawing of stainless steel microtubes. In traditional drawing process, a plunger measure is used to control or constrain the inner diameter of the drawn tube. However, for a continuous multi-pass microtube drawing process, it is difficult to insert a plunger measure into the microtube. Among available techniques, fluid measure drawing or hydro drawing is an alternatively effective method for manufacturing long thin wall tubes. because this method allows the internal fluid to be easily removed by trimming the oil sealed ends after the hydrodrawing process. And a commercial final element software, Deform 2D, was used to simulate the hydrodrawing process. The tube material used was stainless steel 304, an isotropic and electroplastic material model was set for the tube material. Tensor tests were conducted to obtain the flow trace of tube material. Total about 4,000 quadrilateral elements were set for the tube. The minimum element length is about 0.03 millimeter. There are 8 element layers in the same direction of the tube. The mesh configuration in the tube and the geometric configurations between the tube and the die and the drawing force during the hydrodrawing process are shown in these figures. And this study used the Taguchi method with final element simulation to determine appropriately the forming parameters and die geometric dimensions in hydrodrawing process. In the microtube hydrodrawing process, drawing stress shown in figure 1, equation 1, and the all sinking ratio shown in equation 2 are considered as two performance indexes or objectives. Drawing stress is directly associated with process probability. When the drawing stress is too large, the drawn tube is prone to neck or even break. Therefore, confining the drawing stress below the ultimate tensile strength is essential in forming parameter and the die dimension design. The all sinking ratio is the index for evaluating the quality of the drawn product. Minimizing the sinking ratio is also essential in the forming parameters and the die dimension design. In the Taguchi analysis of hydrodrawing process, the smaller the better principle was used for the two indexes. Among the all forming parameters, the die bearing length, the die angle, and the entrance fillet radius, and the internal pressure PI were selected as the control factors. The labels for each control factors were set according to literature reference 6. The 4 control factors and their corresponding 3 labels used in the first drawing pass are summarized in this table. Final simulations were conducted with the labels of the 9 combinations in the Taguchi orthogonal array. The simulated results and the calculated SN ratios are given in this table. The signal to noise ratios for the effects of the 4 control factors on the 2 indexes are shown in figures A and B. These results provide a basis for developing the optimized parameter design that ensures a successful drawing process with minimized sinking ratios. For the effects of the die bearing length, the largest SN value occurred at the level 2 for the 2 indexes. Thus, die bearing length of level 2 was selected. Among the 4 control factors, internal pressure is the factor that most significantly affects the 2 indexes. However, the affecting trend for drawing stress is opposite to that for sinking ratio. The goal of the hydrodrawing process is to produce a thin wall tube with a constrained drawing stress Thus, internal pressure of level 2 was selected. The selected levels for each control factor in the first drawing pass are summarized in this table. The finite element simulation of micro-tube hydro drawing process was conducted again using the selected levels. The simulated inner radius of the drum tip is 0.626 millimeter, or the inner thickness is 0.207 millimeter. That is the minimized sinking ratio is 3.5%, about 0.4% lower than the average value from the 9 cases used in the topology analysis. The simulated drawing force is 311 Newton. The minimized drawing stress is 328 megapascal, about 16% lower than the average value from the 9 cases in the topology analysis. The mechanical properties of the drum tubes after the first drawing pass was successively used as the tube material property in the second drawing pass. The selected levels for each control factor in the second drawing pass is shown in this table. The simulated inner radius is 0.436 millimeter. That is the minimized sinking ratio is 8.9%. The simulated drawing force is 505 Newton. The minimized drawing stress is 732 megapascal. In a similar manner, in the third drawing pass, the minimized sinking ratio and the drawing ratio are 6.7% and 1,216 megapascal respectively. Because of strain hardening effect and the drawing stress needed in the third drawing pass is much larger than that needed in the first drawing pass. This figure shows a structural diagram of the self-developed hydro drawing system, which is composed of 5 major parts. A hydraulic power unit, a taper reel, and oil sealing unit, a drawing die set, a tube from an oil sealing unit, and a drawing power unit. All units were integrated appropriately to ensure that they can withstand the high internal pressure and drawing force during the hydro drawing process. 2 oil sealing mechanisms inside the tube, rear end and front ends, are shown in these figures. This oil sealing mechanism was designed for applications under medium high pressure. In the mechanisms, an oil sealing punch is inserted into a clamp holder and combines an oil seal retaining plan to ensure no hydraulic oil leakage during the hydro drawing process. This figure shows the outlook of the completed hydro drawing system. Before hydro drawing, the tube front end has to be compressed by a specially designed die set to reduce its diameter from 2.0 to 1.6 millimeter for passing through the drawing die hole of 1.66 millimeter in diameter. The middle section is the part that was drawn through the die hole and eventually with a diameter of 1.66 millimeter. In the hydro drawing experiments, for the first drawing pass, the internal pressure was set as 30 megapascal and the die dimension was shown here, which were not the optimized values from the Taoji analysis because of some difficulty in machining of the die made of tungsten carbide. This figure shows the drawing force variations during the hydro drawing experiments and simulations in the first drawing pass. The difference between the simulated and the experimental drawing force is about 27%, which is probably caused by assumed friction coefficient and the trend hardening of the used stainless steel. The deviation between the simulated and experimental final thickness is less than 0.002 millimeter. The simulated sinking ratio of 3.98% is quite close to the experimental value of 3.23%. Finally, some conclusions can be drawn as below. Some examples of applications of tube hydroforming process, such as hydraulic compound forming of rectangular tube, hydroforming of multi-convolution bellows, hydrojoining and hydrodrawing have been presented. The merits or advantages of application of movable dies in tube hydroforming process are decreasing the internal pressure needed, increasing the uniformity of the thickness distributions, improving the formability of the process. And since some manufacturers in Taiwan's bicycle industries have developed their own brand, such as Giant and Merida, these companies could manufacture some components of bicycle using tube hydroforming technology. In the future, applications of tube hydroforming can be adopted to manufacture complex shaped products in motorcycle and bicycle industries in Taiwan. Thank you very much for your kind attention.
Okay, thank you. Thank you, Professor Hwang, the very excellent presentation. According to his presentation, you can see a lot of the research materials showed here. And any question you want to ask him or give some comment? Professor Hwang? Any question? Please.
Yeah. Thank you for a very wonderful speech. For curiosity, I want to know how can you merge the Takuchi method and final element? Yeah, merge them together. Thank you.
I think it's a very good question. Takuchi method usually used for experimental planning, but sometimes it can be used for numerical simulations. It is how to obtain the data, original data. Most of the original data is obtained for experimental. So we use the Taoji method to design the combination, because we have to choose several control factors, important control factors in some level, usually 3 levels. So it's very important. Usually you have the sense for the levels. If we have no sense, we have determined this from the literature. because the level could be result different result, different error. So we have to choose very carefully. But we use the finite simulation as the original data. It's okay. It's okay. But we have to do the simulation again for the real minima index. So we have to after obtain the optimal the levels for the Tauge analysis, we have to simulate or we calculate using minimize optimize the levels. I think this using this kind of application very used very often. So it's different from the original design. Original design is for experiments.
Yeah.
Thank you.
Okay, thank you.
Okay, thank you, Professor Hwang. You want to add something?
Thank you very much, Professor Hwang, and it's very inspiring. I just wonder what is the minimum diameter of the tube that you have produced, the microtube. What's the minimum diameter you have produced?
Minimum diameter.
Yeah.
Oh, okay. In this stage, we can manufacture about 1.0 millimeter for diameter, and thickness about 0.2 millimeter. At this stage, but in the future, we hope we can reach 0.5 millimeter, about one half of the large, the very. But there is many challenge. Yeah, you know, because it's very small, and so it's very small. So how to obtain the material property is another issue. Because usually we use tensor test, but how to design the clamp, so it's another issue, and the material size uniformity is also another issue. So usually we buy the tube material from Japan, because Japan has more, they have very high quality of the material.
Thank you.
Okay. Any the comment or any the questions? Every year that I will check my supervisor the project. Every year he has the four projects. Very difficult, in Taiwan, So why do I check his project? Because I will watch all his topic. If he is doing something, I do not doing something. I need to escape from his topic because I cannot touch his topic because he is very excellent. If I still doing the same topic, I cannot get the project. So I need to find another project, the topic. So every year I still can get the topic, but just two, but he can get the four. So he is very excellent. And any question?
Yeah.
Okay, please.
Yeah. I have one question, but not related to the technology. I saw you conduct a lot of research, yes, and I also know all of those research related to mechanical, to metal forming, technology related, and it seems not easy for the I mean for the female research student, but it seems that you can attract a lot of female research students. I just wondering why. Because all of those research need a lot of energy, need to conduct and then take a long time to conduct the experiment as well as the analysis. Can you tell me why?
Now, in the early stage, when I just come back to Asian National University, and the situation is, as you said, no female students come to my lab. But after 10 years later, many female students come to my lab. Probably I'm very nice. I don't know. I think Professor Jiang also know when we do some cooperation project with Russia, there is one female master students.
Yeah, from the perm.
Come in my lab. At the peak stage, I have 4 female students in my lab.
Oh.
1 year.
Okay.
But I think the topic in my laboratory is not just the need of the strength or force. Very fine simulation.
Okay.
Very fine
Simulation.
Yes, yes.
The design idea.
Yeah.
Design.
Okay.
Usually we ask the male students to do hard labor job, do some simulation, to ask the female student to do simulation. So we can cooperate.
Yeah.
No problem.
Yeah.
Okay, because the time is limited, if you want to ask the professor, maybe you can discuss the data. I very appreciate the excellent presentation. I will give the certificate of the appreciation to him. Okay. Okay. Thank you. Thank you. And now still the